Good day, viewers, and welcome to this lecture. This is a lecture on the correct predictions of the WAEC Physics Practical question number 1, which is the question on mechanics. As you already know, you are provided with 3 retort clamps and stands. There are 3 retort clamps here, 3 of them. You are also provided with 2 meter rules. One of the meter rules is already clamped horizontally here. 2 meter rules, you are provided with, you use the G clamps to hold the retort stands firm to the table. You also have a 100-gram mass here, and you also have a spiral spring. You have a spiral spring. You have an optical pin which I have already placed to the meter rule in this manner. This is an optical pin. Then also you have your sellotape with which you can hold the optical pin firmly. So before we start, let us discuss a little theory just to give you the background of what we are doing and what WAEC is really looking at from people. This system looks something like this. Let me illustrate it a bit on the board. We have 2 vertical strings like this. Then we have a meter rule suspended horizontally from the 2 vertical strings. This system alone forms what we call the bifilar suspension or the bifilar pendulum, where this is a thread, this is another thread, and these threads are suspended. These threads are of equal length. Let's call it L1 or L. We can call it L or L1. This system, when displaced, is going to perform horizontal oscillations. But what WAEC is bringing this time around, they included a spiral spring with a 100-gram mass. So that spiral spring and the 100-gram mass will be fixed at the midpoint of the horizontally suspended meter rule. So you have something like this. We then have another length here, which we can call L2, or if we like, we give it another name, we can call it H. This length is L2. Let's call it L2. So what this forms all together is called, what this does is it performs a kind of oscillation which we call coupled oscillations. Coupled oscillation. This is all about coupled oscillation. Coupled. So it's not going to be the usual single system of oscillation that we have. Instead, this is an oscillating bifilar pendulum, and this is also a loaded spring. And what they are looking at now is for you to determine the torsional effect. When we say torsional effect, we mean the twisting effect of a given material, like a wire or a string. So if this system is displaced horizontally, remember that in this kind of coupled oscillations, there is energy transfer between the 2 systems. So you can displace this one and it will transfer the energy to the first system. You can displace the first system and it will also transfer the energy to the second system. So there is a perfect energy transfer between these 2 systems. So in this case, if the meter rule, which is a horizontal bar, is displaced at both ends in opposite directions and allowed to perform oscillations, that will also happen to the spring. There's going to be a torsional effect. The spring will be turning or back and forth. So this forms a system of 2 torsional pendulums. 2 torsional pendulums. Like I said earlier, because they are coupled, it's not going to be just a single mode oscillation. You are going to have a complex oscillation where in one case you will have angular frequency or angular velocity 1, which is equal to square root of, let's say, k1 all over we use I1, where I1 is the moment of inertia of the first body. K1 is the coupling constant of the first body, while omega 1 is actually the oscillation or the angular frequency when these two bodies are oscillating out of phase. There's going to be another angular frequency when the two bodies are now oscillating in phase. At that time, when we do the experiment, you will notice that the oscillations will be faster because the two bodies are in phase. In that case, you have W2 equal to square root of K1 plus 2K2 all over I2. Now, in this case, K2 is the coupling effect of the second of the spring. I2 is the moment of inertia of the suspended 100-gram mass. And you know that you can actually determine the moment of inertia of any regular object, even if the object is not regular. There is a way to determine this. So, as we know already in physics, once you have two frequencies that are close, it forms what we call a beat frequency. And how do you get the beat frequency? The beat frequency is obtained by subtracting one of the frequencies from the other. So it is possible for us to subtract the omega 1 from omega 2. And when we do that, it is going to lead us to a complex equation, or not really a complex equation, to an equation, a straight line equation that can help us to determine how the period of oscillation of this system varies with any other quantities. In this case, if you notice, they have asked you to provide only one mass, so it means that they cannot be changing this mass here. The only thing that will be changing here is the length of suspension L1. While by the time we practice the experiment, we can begin from L equal to, let's say, 70 or 80. We drop it. If we start from 80, we drop it to 70, 60, 50, 40, until maybe we'll get to 30. You will notice that the period of oscillation decreases as the length also decreases. Now let me write the equation. Please, the origin of these two equations is actually some tedious mathematical calculations. These are things that you do in analytical magnets. So I will not take you through the origin of this. Alright, like I said, the origin of these two equations is a bit tedious. It's actually from analytical magnets. And if we want to go through all of that, the video is going to be very, very long. So if you take the beat frequency, since you already have this as an angular frequency and this as an angular frequency, if you take the beat frequency, you can also obtain the beat period from there. Don't forget that period is actually the reciprocal of frequency. So if you rearrange these equations and make substitutions such as the fact that this torsional constant being inversely proportional to the length in each case. So this will give you an equation like this. T squared is equal to 4 pi squared all over 1 into L1 divided by alpha 1 into I1 minus I2 minus L2 all over 2 alpha 2. You actually do not need all of these lengthy equations. But what this equation tells you is that the period of oscillation of this system is directly proportional to the length of suspension here. It is also proportional to the second length as well. But in the experiment, you are given only one mass, so there is no possibility of changing this length. As long as the spring constant is not exceeded, this length will not change. For that reason, what you will be varying is L1. So you can plot a graph of T squared against L1. Alternatively, when you take the reciprocal of both sides of this equation, then you'll be able to plot a graph of t squared inverse against L inverse. So let me give you a little demonstration of what the oscillations will look like. Okay, let's turn the camera this way and see what it will look like. So when I suspend 100-gram mass from this spring, then this is what happens. With this, you can measure with the vertically suspended meter rule. You can measure the length L2 as shown on the board. So if you have your stopwatch, I have a digital stopwatch here, you will simply displace this horizontal meter rule in the opposite direction like this. You displace it this way. Once you release it, you notice that at some point the oscillations are very fast. Okay, that's when they are in phase. When they are out of phase, the oscillations are slow. When the two systems are out of phase, the oscillation is slow. When the two systems are in phase, the oscillations are faster. So you take the time for 20 oscillations. And I advise you do it 2 times. You take time t1 and take time t2, then you get the average. When you get the average, even if you do not state the correct precautions in your experiment, the fact that you did it 2 times is a precaution, and you get a mark for that in your precaution. So I did this already, and for different lengths, I began with 30, 40, 50, up to 70. So I'm going to give you a table of what, I'll show you a table of what your own should look like here. So please turn the camera this way. You should have a table like this. You should have a table like this. You should have a table that looks like this. I have serial number, maybe 1, 2, 3, 4, 5, as the case may be. I have length L1 in centimeters, 30.0, 40.0, 50.0, 60.0, 70.0. Then I have time t1 in seconds. I have time t2 in seconds. I have t average, which is t1 plus t2 all over 2, still in seconds. The table continues. I have period t, which is equal to small t all over 20, since it's 20 oscillations. Then I have this, and then lastly, t squared in seconds squared. Like I said, you may also expand the table so that you have t squared inverse, which is 1 all over t squared. In case you are asked to plot a graph of t squared inverse against L inverse. So this is what your table should look like. And when the graph is plotted, the graph should be of this nature. You should have a straight line graph of this nature. You have a straight line graph of this nature. From this graph, you have a negative intercept here. You have a negative intercept C. And if you check the equation I wrote before, I said t squared is equal to 4 pi squared all over 1 into L1 all over alpha 1 I1 minus I2 minus L2 into 2 alpha 2. So this is what we have here is the intercept of the graph. Don't forget that the straight line equation is always of this form: y equal to mx plus c, plus or minus. So in this case, the intercept is a negative intercept. And with this, you can always, when you already know the length L2, which is the which is the length of the spring. Then you can calculate the torsional constant of the spring used. So, if you want a video of how the graph should be plotted and the questions that are likely going to come with this, with the precautions, just put it in the comment section and I'll do another video on that. Thank you very much.